Problem 16. To make the sum of the two 5-digit numbers maximum, we need to put the largest digits on the left side and the smallest digits on the right-hand side. So let's assume from left to right, the 5 positions are labeled 1, 2, 3, 4, 5. And the first position on the left side, for the two numbers, we need to put either 9 or 8. And the second position, we need to put either 7 or 6. And then the third position, we need to put either 5 or 4. Similarly, the fourth position, we put 3 or 2. And then the last position are left with 1 or 0. Now, it doesn't matter the order of the two digits, which one will be the first number or which one will be the second number. So let's look at the answers. For the answer A, 7 is in the first place, so this does not qualify. And answer B, 8, 6, 7 is in the third position, so this does not qualify either. And C, 8 is in the first position, 7 in the second, 4 in the third, 3 in the fourth, 1 in the last position, and this one is correct. And let's look at D, 9 in the first position, 6 in the second position, 2 in the third position. That's not right. So this one does not work. And E, 9 in the first position, 7 in the second, 4 in the third position, 0 in the fourth position. That's not right. So E doesn't qualify either. The answer is C. Problem 17. The square is with integer side length and is cut into 10 small squares, and 8 of which have area 1, so their sum should be 8. And 8 is part of the large square, and if we left with two squares, the smallest possible area of each square is 1 plus 1. And because the sum 10, the square root of 10 is not an integer, so this does not qualify. And let's assume the two small squares have area 1 and 4. And 8 plus 1 plus 4 equals 13. And again, the square root is not an integer. And similarly, the next largest possible value for one of the square is 4 plus 4, and that equals 16, and the square root of 16 is 4. Therefore, the smallest possible value of the length of the larger square is 4. Problem 18. For this problem, if we try to find the prime factors of each number, it would take too much time. Therefore, let's first look at the two prime factors that are larger than 50, and they should be 53 and 59. We multiply 59 by 53, and that gives us 5 multiplied 9 equals 45. So that's 7, 2 here, and 1. So that's 3,127, and this is answer A. So in a jar of red, green, and blue marbles, all but 6 are red marbles. That means green plus blue equals 6. And all but 8 are green. That means red plus blue equals 8. all but 4 are blue. That means red plus green equals 4. Let's assume these are equations 1, 2, 3. Now we use equation 2, subtract equation 3. We get b subtract g equals 4. And we assume this is equation 4. And we use equation 1 plus equation 4 on both sides. And that gives us 2b equals 10, which means b equals 5. So we substitute b into equation 1, we can get green equals 1. And we substitute b into equation 2, we can get r equals 3. Therefore, we use 5 plus 1 plus 3, and there are total 9 marbles in the jar. The answer is C. Problem 20. In this problem, notice that each denominator subtract its corresponding denominator equals 14. So in this case, we use 1 subtract 5 over 19, it equals 14 over 19. And 1 subtract 7 over 21, that equals 14 over 21. 1 subtract 9 over 23, that equals 14 over 23. Now we can say that because the denominator is 19 is smaller than 21 and 21 is smaller than 23, therefore we know that 14 over 19 is larger than 14 over 21, larger than 14 over 23. And so the original numbers will be 5 over 19 is smaller than 7 over 21 is smaller than 9 over 23. And the answer is B.